Okay, so let's start. Let me share my screen and let me know once you can see. You can see the screen, right? Yes, or no, you can type in. Okay, so then let's start. Um, can you at least confirm if you can see the screen?
Yes, sir.
Okay. Okay. So today we'll be going through the basics of neural networks and and how do we implement a neural network, say in PyTorch. Um, that will be the high-level part of the notebook section. And as usual, we will be solving six problems related to the topic. Okay. So yeah, so let's go through the this thing, PyTorch. Right. So PyTorch is a Python-based scientific package uh, for the um, deep learning researchers and to optimally use the power of GPUs. And so it has many similarities with the NumPy package, which we had discussed in the first two. Okay, so yeah, so basically, if you the objects in the torch we call as tensor. In NumPy we used to call as array, NumPy array. So here is the torch tensor. So if you want to create a torch tensor from list, right, yes, you can do torch.tensor of that list name, then it will be converted to a tensor, right? And even from this tuples also you can convert to a tensor. And yeah, there's another variation where all ones that is an NumPy array that is also can be converted to tensor by using this torch.tensor. Okay, so these are the ones of pi 3 means you create all one vector of dimension, not all one tensor of dimensions, pi cross 3. And similarly, cos dot zeros of 2 will give you uh, this thing, uh, tensor of size 2, right? This one. And yeah, this is an empty tensor. The last, which is of dimension one, one, and five. Some thing on random numbers as we discussed similar to NumPy. So this is uniformly distribution. I mean, these numbers are picked from uniform distribution from 0 to 1, basically. Right? So this is nothing but a tensor of dimension 1 cross 3. Right? So yeah. And rank n is normal distribution, which is nothing but the Gaussian distribution, and the dimension is 3 cross 4. And zeros underscore light means it creates a tensor of size A and properties of size A, but entries are zeros. And similarly, RAM like C, it will give you a uniform distribution, but is similar to this distance. So yeah, that is what it is here. And yeah, so now to replicate to maintain some determinism in the random numbers, we have something called as C. So this is to avoid the randomness, right? So in toss, for NumPy, you have something called as np.random.c. And for toss, you need to set all these things if you want to run the experiments in a deterministic method. We'll see the examples for it. And yeah, so when you set the C to true, no matter how many times we run, we'll get the same thing, right? But if I set it to false, it will give us a different thing. Right? Each time it will be different, right? But if you set it to true, no matter how many times you run, you will get the same thing. Okay, so you can ask any questions. You want to stop anywhere, you can ask me. I can stop. And this toss dot arrange is same as np dot arrange, right? Here you have this thing, starting point, ending point, and how many steps it is one needs to increase, right? So it's going from 0 to 9 steps of one. Similar to np dot clean space, um, similar to np dot clean space, we have something in toss dot clean space, right? It's the same thing. Um, But the only difference is here, torch, you get the tensors and numpy called and numpy called as numpy arrays, and torch you can access they manipulate the tensors using GPU, that which you can't do with the numpy arrays. Okay, so what are the common operations in PyTorch? Right? Yeah, I think you have already seen this. This is torch.ones of PyCross 3, create a PyCross 3 tensor or matrix with all ones, and this is a uniform distribution 0 to 1 size 5 cross 3, and yeah, these are empties. When you add the same thing, you get this. Okay? So when you run this, you get uh, a plus b. Uh, Basically, it's a point-wise addition, right? You can add two matrices of the same dimension. That's fine. Matrices can of similar dimension can you can add, but yeah, you cannot do matrix multiplication with the same dimension, right? So this is element-wise multiplication. So each entry of A is multiplied with each entry of B at that particular location, and that entry is being recorded into a tensor of called D. Okay, and yeah, it's the same operations as NumPy, right? You can add two tensors, subtract, multiply, divide, and exponential. Division one needs to be careful to avoid zeros in the denominator. So, what are the operations we can do on a tensor, right? So this is this some uniform random distribution you pick up equals 3 matrix. Each entry is picked up from a uniform distribution. That's what I mean. And yeah, so this is the first operation is printing that. And the second is when you do x dot sum, it sums up all the 9 entries of this tensor, right, which you get as 5.9. And when you do the sum of axis 0, it sums along this axis. So for each column, it sums along this axis. So to be precise, it sums 0.515191 this one 0.98, 0.69. Again, it will sum this, and this. Okay. So basically that's what, right? Sum of the columns. So each column is being summed. Again, if you just switch the dimension by specifying axis one, each row is summed, right? And when you say x dot mean, it computes the sum of all the entries and divides by 9. So basically, this is what it is. You divide by 9. Same thing, mean of axis 0, sum divided by 3. Yeah, divided by 3. You get this. Okay, any questions you can ask and then stop me. And um, okay, so yeah. Now, if you want to multiply, actually multiply to this thing, to matrices, right? You can do this. At the rate symbol is something that you can do. And plus is the element-wise addition. Addition is anyways element-wise addition. And so it is multiplying two matrices, A1, A2, and then add. Other operations that you can use is matmul, matmul of this A1, A2 will give you the same thing. Yeah, this is, and how do we do dot prod? So basically, dot prod is very simple. It's just torch dot of B1, B2. It just computes the dot product of these two tensor. Dot product is nothing but this element-wise multiplication and then adding it, right? And how do we manipulate tensors? How do we access tensors in PyTorch? This is also bears a lot of similarity with the way we deal with NumPy. Right? You want to print the last index, you can access it by using -1. Right? It gives you 9 and 1 to 3. So it picks 1 and goes up to 3 without including 3. So 1 and 2. Right? And -2, it prints up to -3. So last two will be discarded. Any questions on this?
No, sir.
Okay. And yeah. So this is a 5D tensor that is being created from uniform random distribution, and we'll see what how these shapes this thing, right? Assign. So this is a 5D tensor, and so we want uh, if someone is asked what is the first entry of this shape of the first entry of this tensor, if you do x of 0, right, and so you get a tensor of 2, 3, 4, 5, right? This is the size. If someone asks the shape of x of 0, comma 0, 0, 0, so it is 0 and 0. So you can treat this as let's say if you forget about this thing, you can treat this as 1 cross 2 matrix, and each entry of the matrix is the tensor of rank 3, 4, 5, dimension of 3, 4, 5. And that's why it is 0, 0, 3, 4, 5. So if you put 0, 0, 1 and print the shape, it will still be 3, 4, 5. If you put 0, 2 here, you'll get an error because you cannot access anything beyond 2. So 0, 1 is the max you can access on this index. Right. So similarly, 0, 0, 0 will have a dimension of 4 plus 5. So torch dot arrange of 12 will give a tensor of one-dimensional tensor of length 12. And when we reshape it, it reshapes to 6 cross 2, as mentioned by the arguments in the reshape function. Right? Basically, it does a reshaping on the row wise. This, what I mean is, if this is my original tensor, right, the torus dot array. So first it creates row wise thing. So it creates its columns and it splits across row wise. So first it writes 0, 1, next 2, 3, 4, 5, and so on. Yeah. And once you flatten again this thing, right, it will become this puts everything in one layer. And again, you reshape it to 3 cross 4. Again, you see 3 cross 4, it reshapes by row 1. So first 0, 1, 2, 3, 4 are put in this thing, uh, first dimension. 3, 4, 5, they put it in second dimension. The other. And yeah, so U and reshape are the two functions that can do this for us. Now, squeezing the tensors is when you want to collapse an unnecessary dimension, right? You can use the squeeze function. What I mean is this thing. Now here it's a one D array. Sorry, it's a 2D array of size one row and 10 columns. One can view that way. So after squeezing it, um, we will get a 1D array basically. Right? It's like x of 0. We'll see that what I meant. Um, So here uh, we create a 5 cross 5 tensor of from random normal distribution, and we want to unsqueeze this. We want to append one more dimension, right? We can specify that by using unsqueeze, and this one is you specify which dimension you have to put it. So it creates a extra dimension in the specified location, in the first location, basically. Now we want to swap the axis or do transpose operations, right? It's very simple to do it in the torch. You just have to permute the indices. That's it. So what I meant is this: if the input tensor is 3 cross 48 cross 64, after permuting, it will be 48 because first index is 48 here, 2 is 64, and this is 3. Last is 0. That's why the shape is like this. Right? Again, concatenation operation is also very simple. And here we are creating 0 to 11 numbers and reshaping it to 3 cross 4. And we are creating a 3 cross 4 tensor here explicitly. And we want to concatenate along axis 0 and axis 1. So axis 0, it makes 6 cross 4 matrix, this one. And axis 1, it makes 3 cross 2, 3 cross 8, sorry. Okay. And yeah, so now we can convert something from numpy to tensor and tensor to numpy. Right? So let's say this is a toss tensor, and you want to convert this to numpy, right? This is x dot numpy, and yeah, this is a toss tensor. You converted it to numpy again. You converted it back to tensor by using toss dot tensor. Okay, so if a system has a GPU installed, then we can detect it using the torch APIs or CUDA is available, right? If it's there, it will automatically detect conflicts true. So in my system, it's not there, so it is false. Okay, and yeah, so this one can set it to device. So basically, you always have to write something like this. So if GPU is available, it takes the GPU, or else it takes the CPU. That's it. Okay, so far, yeah, it's just conversion to GPUs or CPUs. So basically, when we add two tensors, they both have to be on same devices. CPU one cannot be on CPU, one cannot be on GPU, right? So that needs to be taken care. Here we will not get the problem because the laptop to which I am presenting it doesn't have GPU, so it's always CPU. Okay, so yeah, let's go to this thing. Neural networks part. And we create a data set. We'll show what is the data set shortly. Yeah, so this is the data set. Okay. Here we have points in a 2D space. And the orange points are labeled as the class belong to class one, and the blue points are labeled belong to class Z. And yeah, we need to learn the mapping of given a point, we need to say now it belongs to class one or class zero. Because so that is what we will see now. You know what is perceptron? If people are aware of perceptron. Yes or no? Otherwise, we can briefly go through. Okay. Okay. So you want me to go through before we do something on that?
No, sir.
No, what I'm saying is, do we want to, do you want me to just briefly review what is that about perceptron, or we can um, go ahead with this thing? No, what I mean is, do you want me to give an overview?
Uh,
Okay, okay,
inform,
fine,
sir.
fine.
Inform.
Okay, yeah. So basically, let me show you. Fine. Can you see this screen?
Yes, sir.
Yeah. So, um, perceptron is a linear classifier. Basically, it's a classification algorithm, and I'll put cross and O's to denote class zero and class one. O means class zero, plus means class one. Okay. So we need to find a linear classifier, right? Which separates these 2 points, data points, something like this. Right? It separates this. Now, because we can see the data and we can say that they are separable and we draw a line. So how does a machine finds out? Right? This is something called as perceptron learning algorithm. Um, right. So what it does is, um, so let's for convenience, let's call this as class one and this as class minus one. Okay.
Yes,
So
sir.
you have a data point X. This is lying in 2D. 2D we denote usually as R power 2. And we need to learn two things here, W and B. B is the scalar, so R power 1. And W lies in 2D, R power 2. Right? Now, our classifier is nothing but this thing. Now, we would like to declare it as the positive one if it is greater than 0, and the negative one if it is less than 0. Okay. So, um, when do we make a mistake? So how do we quantify? Let's call this as y hat, our prediction says y hat, and y as the true label. Right. So for an example, say if example, let's call as I example I, and we have this thing y as positive, and y hat is also positive, right? So this is the correct prediction because the true one is saying it is plus one, and our algorithm is also outputting plus one, right? So it's the correct prediction. So there will be a mistake only if this product is negative. Okay. So perceptron will, so the algorithm of the perceptron is once a data point comes, data point is, well, let's denote this as x, this as xi and yi. Check if this is negative, if this quantity is negative. That means we are making a mistake or not. At time t, at time t means let's say yeah, let's say at time t we got this example, and at time t our weights are wt and bt, right? Now, if our wt and bt is able to classify it correctly means this one will be positive. The product will be positive. Okay, so this one will be positive. Then we don't need to update wt and bt. So for the next time step also we will take the same updates. Okay, but let's say if there is a mistake that's been made, so simply we will update this thing wt plus 1 is equal to wt plus whatever is the sign of that example, right? Y I times xi. xi. Okay, so this is the update rule. That's it. This is perfect. So essentially, we are minimizing a loss here that is nothing but minus y times y. And B, we can always assume that B is absorbed into W and X is nothing but augmented with 1. So what I meant is this. X you can always write as X and 1. And B and this W you can always write as W, the original W and B. That's it. Dot product and we're done with it. That's it. Any questions? You can ask because I can't see the chat often.
Yes, sir.
Um, right? Any questions on this?
No, sir.
Okay. Okay, thanks. Okay, so this is what is perceptron and this is what is being coded here. Okay, so here these are the examples that are given us to learn the W's and D's. Okay, and this is the training set that is shown pictorially, and we are given a test set. So basically, what the way we test is we are given this thing to learn W's and D's, and once you learn W's and D's, you want to check how well your W's and D's are have learned the data. So this is the test set, and yeah, so this is what it is. Yeah. So this is our this thing. Right? So we have learned this line. Okay. So one more thing about perceptron is as long as the data is linearly separable, perceptron correctly finds the hyperplane separating the positives and negatives. Okay. So this is what I have observed here because it was able to the data was separable through a hyperplane and we are able to separate it through a line. That's it. Okay. And the same perceptron implementation on the torch, PyTorch. No, nothing different here. We get the same thing. Okay. Okay. So you guys know about the feed-forward neural networks and what does the back propagation mean? Or you want me to give a quick very overview of this thing and gradient descent? Okay, so no need for going through the neural network part, right? We can directly solve go over the notebook, right? Okay, cool. Yeah, so basically here we just say what is the gradient descent, right? And given any function z as a function of variables x and y, gradient vector is nothing but the partial derivative of the function with respect to the variable x. Here we have two variables x and y, so it will be a vector. And similarly, the chain rule is the traditional thing. Like we first differentiate with respect to g and then differentiate with respect to h. And yeah, yeah. Same thing here we are just showing. And one more thing to remember is gradient always points in the direction of higher values. Okay, the direction in which the function is increasing. So let's say blues are increasing here and say the others are decreasing. So if you point if you evaluate gradient here, it points in this direction, right? The where the function is increasing. And yeah, so basically the gradient descent algorithm is nothing but because we know the gradient points in the direction where the function is increasing. If you take the negative of the gradient, then it points in the direction where the function is decreasing. So that's the gradient descent algorithm. So let's say we have our weights at time t, and we observe that we got some gradient. That means this gradient, it means gradient in that direction, it is increasing the function, the loss value. And that's the reason we put a negative sign here and we add it to the existing. ways. So in that way, we go along the direction where the function is decreasing. Okay, so that's the gradient descent. Okay, so in PyTorch, we don't need to do all this manual computation of the gradients of the neural networks. It can get complex and error prone as well. So we have something called as PyTorch AutoGrad, where these algorithms are implemented in very efficiently, and we can use it very efficiently and easily. Okay, so yeah, so here uh, we just show right how this how we can use this autogram versus the brute force comparison of the computation of the gradient. Okay, so um, yeah, so we have given this thing, say a data point W transpose X plus B, and we pass it through a nonlinearity panels. Okay, and here Y is the reference values. So it's a regression problem. It's a traditional regression problem. And we are evaluating the square function, and we call that as loss. Right? We want to learn W and D. That's why they are highlighted as parameters. And by minimizing the loss functions, we need to learn these W's and D's. Right? So what are the gradients of loss with respect to parameters like W and D? Right? We need to keep invoking these things and update the W's and D's. Okay. So these are the helper functions that to, you know, here we create some tensors, right? Which so we need to be careful to assign this thing, request grad into. Okay, and make a forward pass, right? Forward pass is also very simple, right? Manage of this thing, W transpose X plus B, right? This part, and this is our predicted value, and our loss is a squared loss, right? This is nothing but the true versus prediction whole square, and this is our loss. And yeah, let's see. Now we come to the back propagation part, right? And so we have given this prediction thing here, right? And we set this to this thing, the values to this equals grad to true, right? So it has we can compute this gradient basically. So if you print what is the function that is associated, right? It will give you the last function in the entire sequence of this. Okay. For square laws, it was given this power backward, and for this thing, prediction, which is the tan h on the W transpose X plus B, it has given this thing. Right? And this is the brute force comparison of the loss, right, with respect to W and B. And now we match the torch dot autograd gives the same answers as manually computed values. Right? Answer is it indeed does. Right? So this is the analytical way of computing the gradients. Okay, and the same formula has been implemented here. That's it. And we compute the gradients using PyTorch this autograph for loss dot backward, square loss dot backward. This is important. Dot back. Once we compute it, we get the gradients through this thing, right? The graph, and basically this is the model. Call it as graph. Dot w dot graph. That gives us this variable dw similar to db. Here we check if that analytically computed gradient is matching with our PyTorch system. If it matches, so it's true. That's it. Okay. So we need to call this once. Okay. Um, yeah. So same thing, neural networks backpropagation. We see other aspects now. Like here we are not using any GPUs, right? So we always see the CPU thing in because my laptop is no GPU. Okay. How do we train things in Python? Let's say we want to learn this pattern, right? Given an input and we want to find why. So something like sine wave or something, approximately sine of a. So we call it as a wide net, a neural network. So we use this module, NN module, to create our models. And this is any custom name. And we have to define this function for all the any model we create like this. Okay. And yeah, so this is the height 12 width height function. So to be precise, it is something like this. We have one neuron and a bunch of neurons here, and we have something a single neuron. So it's 1 cross 512 here and 512 cross 1. Okay, so Tanish nonlinearity is used here, and yeah, that's it. And we will use a regression loss, that is mean square loss. And here is the way to print the network. It has a linear 1 to 5 to 1. So use the nonlinearity Tanish and then 5 to 1. Right, so now you train it, right? So this is a loss that how that loss is converging to zero that one can see by using the gradient descent algorithm. And this is the prediction. Right? The prediction you can see it is pretty continuous because the function is continuous, the Tanish. And this is how it puts the data. Okay. And now let's do a typical image classification task on a digit data set. A digit data set is nothing but is a MNIST data set, right? So yeah. So here we download the data. I will show how this data set looks like actually. Just give it a minute. It's loading, right? So these are the images, sample images that's been loaded, like 6, 3, and 7. And same thing like the earlier one, we create a module by inheriting the thoughts and end dot module. Here the input dimension is 784, output dimension is 10. Okay, same thing. Here we have, say, because it's an image of say 28 cross 28, right? We have height and width in an image. So we vectorize this, right? So we convert this to a vector. Means from this square image, we squeeze it basically, right? We get 784 input, and this is passed through uh, this model of length 784, right? And we get a scalar y. So basically, just nothing but W transpose x and X is from image we convert it into a vector of 784 plus 1. This is 1 cross 7. That's it. And this is Y. And I think there is non-linearity also that's being used. And okay, as of now, I think there's no non-linearity here. And yeah, this thing Y here it is of 10 dimensions because we have 0 to 9, 10 classes to classify. Right? So basically, after we get this thing, right, this W will be 10 cross 784. Okay. So W transpose X plus B. Now we do something called a softmax operation. So you guys know what is softmax? Yeah, just an other way I can explain what it is.
Yes, sir.
Okay, good.
Yes, sir.
Um, then you know why it is called softmax? Okay, maybe I can emphasize this thing. So let's say you have 1, 2, 5, minus 1, minus 2. What is the max operator? Max operator will give me 5 here, right? And it completely ignores what is happening here. No information, right? What the softmax do is it takes this thing. It exponentiates it. E power 1, e square, e power 5, e power minus 1, e power minus 2. So here we'll get e, here we'll get e square, here is e power 5. So whichever is maximum, you get more weight to this, right? It's a softer version of this thing, actually. It doesn't throw away any information on this. It preserves some information on this. That's why it's called software version of Max. Okay.
Yes, sir.
Yeah. And that's it. So we take softmax here and yeah, we just implement the gradient descent here. And yeah. Yeah, so these are typically, some of the loss surfaces that we may encounter in optimizing determining loss landscapes. So if you see the direction of minima is somewhere, it is something like this, right? And here the gradient, if you move in this direction, you get gradients pretty steep. And yeah, so what happens is in these situations, the local minimum, the actual minimum can be somewhere down the line here in this direction. Our gradients are typically more biased to going here rather than here, right? This is some thing one has to keep in mind. And that's the reason just SGD instead of SG as just SGD people have proposed Mr. or SGD with momentum and other variants. Right? So here we'll see if we optimize such a kind of landscape, how how these things go. You can say just like LGD, right? Each dot is a time step. It takes quite a long time to go and converge to minimum. Whereas if you say take momentum takes little, even momentum also takes time for this kind of setting. But if you say anagrad or RMS Pro, right, they are pretty much there. Right? They don't take much time to find the option. Okay, so another thing is the sleep optima, right? Let's say um, yeah. So here also in this kind of situation, we need to be careful while sorry, setting the learning rates and all, right? So otherwise, we end up escaping these optimum points, right? So we just that. Um, and yeah, so this with this we are done with today's notebook. We will go to problem section. Anything that you want me to tell. Otherwise, we will simply solve problems. Anything? Okay, so let's go to the problems part. Okay, so here we are given a simple perceptron and an R power 4 to 4, I mean that four-dimensional perceptron. And we use tan as a nonlinearity. And input vector is this thing and corresponding weight matrix is this. And we want to compute the derivative of this tan output. So please can you allow somebody who is waiting? I will need to keep moving this problems basically. And we just ignore the bash into zero for now. Right, so this is nothing but the dot product of W and X. We get Z as this, and tan H of Z is this thing, and the derivative of this is nothing but 1 minus tan square of it. That's it. We just need to substitute Z here, and we get this one. Okay. And which of the following are true regarding the dropout on the network performance? So dropout is a regularizer actually, right? It basically adjust the activation level so that output okay one can just see what dropout during training causes network to overfit. This is incorrect because dropout is a regular result. It doesn't cause training to overfit. Okay, so during the training of dropout, network adjusts the activation level so that output remains consistent when the dropout is not applied during inference. This is true. Right? And dropout during training leads to smaller final model size. This is wrong because dropout just punches the weights only during the training. During the inference, all the parameters have to be tested. Okay, the final output during training is multiplied by the dropout rate to maintain the same expected output. When dropout is not applied during the inference. Yes. Yeah. So now, when we train a neural network, we have a bunch of techniques to prevent overfitting. These are called as regularization. L1, L2, and batch normalization. Batch normalization typically not be considered as regularizer. Um, right, so this is an incorrect statement because L1, L2 can be used along with dropout. Now, L1 regularization, yes, is indeed used as fast rates, and fast normalization never slows down the training, and it in fact accelerates the training. Um, Accelerating, I meant it goes to a better training loss than without using the batch normalization. And yes, we need to operate batch normalization differently during the inference phase. So we don't do batch normalization, update the this thing, right? The buffers of running mean and variance given to me. Right? So the correct answers are two and four. Right? And this is a simple exercise on the using the adagram RMS prop algorithm, right? And we are given we have to find the parameters at theta plus one when we are given at theta t what is the parameter, and we are given aggregated gradient and gradient accumulation value at in the of the history, learning rate, decay rate, and some constant, right? Yeah, so this is the hmm, RMS prop algorithm, right? The current step output is it's not the exact current step output. So here we are tracking the second moment of the weights basically in using some momentum. Right? And while adapting the weights, we just scale scale down when the gradients are high. So that's the this is the update rule. We can just simply plug in the values here and we can get the final answer as well. So you need to be familiar with these update rules to answer this kind of questions. Okay, so we have a neural network and we want to see how the batch size impacts the training and computation. Okay. Batch gradient descent uh, is so there's something called as full batch gradient descent, batch gradient. So okay, I think full batch here is a batch complete. It's a gradient descent using all the data points. Right? So this is true. You cannot use the complete data points as a match when dealing with large data sets. And SGD often leads to a noisy path. And yeah, this is correct. Right? SGD often leads to a noisy path, and it can help in escaping the local minimum. Minimatch gradient descent is faster compared to the batch gradient descent because it takes mini batch as compared to the entire data. And stochastic gradient descent, it is false because it cannot guarantee faster convergence. And using smaller mini-batch size in mini-batch generally increases the variance of the parameter update. That's true. So you can see, right, batch gradient descent, the complete data, and we are moving on to a loss cycles towards this. There's no noise in the variance. Mini-batch, yes, there is a noise. There's a variance in your ingredients. That's why it's going up and down. For stochastic variance, very high variance thing, right? That's why it takes a lot of time to convert. And this is something called as mix-up augmentation. You guys are familiar with mix-up? Yes or no? Yeah, so basically, I'll go over quickly once we solve this. So mix-up is a kind of augmentation technique, data augmentation technique to the generalization of the model. I mean, yeah, improve the model performance. So it's very simple. It's given X two data points, X2 and two labels. Mix-up, we can create a mix-up new set of data or mix-up data by just following the this thing convex combination of the data points and the labels. Yeah. Yeah. I, any questions on this?
No, sir.
This is fine, right? Okay, is straightforward, I guess. If there are any questions, please ping me. Let me know. I'll try to answer. Otherwise, we can end them.
Yes, sir.
Okay, thank you.
Yes. Okay, sir. Thank you.